Hello, good morning everyone. My name is Venkat Venamala and today my topic is understanding branches and designing branch predictors for the high performance microprocessors. Introduction. Branch prediction is one of the most important factor in microprocessor. Increasing memory latency may affect the deeping problem. Branch prediction is one of the most important, effective, and correct path. Microprocessor designers need to understand the branches. Designers also need to know that what is meant by prediction algorithm. Here is the table that represents the description of benchmarks and their input sets. Some of the benchmarks are Compress, JCC, Go, iJPEG, M88KSIM, Perl, Vortex, XLisp. Each benchmark is having its own description and test set. Each benchmark has its own number of dynamic instructions and number of dynamic branches, number of dynamic condition branch and static condition branches. Branch characteristics and behavior. In these three branch properties are investigated. They are type, frequency, taken rates. These are helpful in understanding the branch behavior. These branches are divided into conditional and unconditional branches. Unconditional branches are further divided into immediate branches, indirect branches, and returns. Immediate branches have the target address encoded in the branch instruction. Indirect branches get their target address from a register. Returns get their target address from a link register or a stack. The diagram represents the distribution of static branches by execution frequency. By observing the diagram, we can say that the most branches are executed only few times during the run of a program. 53% of branches are executed 99 times. Only 11% of all branches are executed 10,000 times. By observing this diagram, the weighted distribution of static branches by taken rate. 28% of all branches are static branches, 95% taken, and 60% branches are strongly biased in one direction. Looping and other schematic behavior. We saw in the previous section that 28% of all branches are always taken or always not taken. Many of the remaining branches follow repeating. The pattern that is repeating can be any string of outcomes repeated over and over. A representative example of this type of pattern is 110, 110, and 110. Here 1 represents taken outcome, 0 represents non-taken outcome. The correlation between the branches. The outcomes of branches that are close together in the source code are often dependent or related. Two branches are said to be correlated if there is a reciprocal relation between their outcomes. There are two obvious reasons for the directions of two branches to be correlated. Here is the example of the correlation. This is the condition of the two branches are based on the same or related information. Dynamic branch prediction schemes. Dynamic branch prediction scheme is based on two interacting mechanisms. It's branch outcome predictor and branch target predictor. Branch outcome predictor is to predict the direction of the branch that is taken or not taken. Branch target predictor is to predict the branch target address in case of taken branch. These modules are used by the instruction fetch unit to predict the next instruction to read in the iCatch. Basic branch predictors. The branch prediction algorithms that are easiest to implement are those requiring no history or only a single level of history. Always predict taken, since a taken outcome is slightly more likely than a non-taken outcome. This can be used as a very simple predictor. If the branch displacement is positive, predict not taken, otherwise predict is taken. The compiler can then arrange the remaining branches such that the most likely path is not taken. Branch history table. Branch history table is also known as branch prediction buffer. Table containing one bit for each entry that says whether the branch was recently taken or not. Table indexed by the lower portion of the address of the branch instruction. Prediction hint that is assumed to be correct and fetching begins in the predicted direction. If the hint turns out to be wrong, the prediction bit is inverted and stored back. The pipeline is flushed and then correct sequence is executed. Branch target buffer. Branch target buffer is a cache storing the predicted branch target address for the next instruction after a branch. We access the BTB in the if stage using the instruction address of the fetched instruction to index the cache. The predicted target address is expressed as PC relative. Conclusion. As discussed about several aspects of branches and branch prediction, the misprediction rates varied from over 40% for the worst static predictors to less than 4% for the best and the costliest of the dynamic predictors. Finally, we identified some of the problems in future branch prediction design. We, represent, we presented possible approaches to address these problems, but also showed that all of the approaches have some disadvantages relative to the ideal case. Here are some references that I have used in completing the presentation. Thank you.